Okay, uh, I think we will start the session slowly as people are coming in. But I would already like to welcome everyone to the session number 8, which is on theory, development, and use. Actually, I think it's a very interesting session because it's the papers demonstrate somehow each of them the relevance of some particular theory to some very important information systems engineering problems. And this, I think, also fits very well with the motto of the overall conference, namely intelligent information systems. So here the intelligence essentially adding the knowledge gained from theory to improve methods that are used widely in practice. So I think for the conference they are quite relevant, and actually several of the papers have improved. I apologize for the authors because some of them I shepherded a little bit and gatekeep, so that I added some additional work for you. My name, by the way, is Sjaak. I'm a professor at the RWTH Aachen University in Germany, and also a director of the Fraunhofer Institute for Applied Artificial Intelligence. So this university, one floor up from me, as we discussed already before, is sitting with Van der Aalst, who got here a little while ago. So we have nice collaboration since then. Yeah, with I think now we have also all the speakers in the room. We have 3 very interesting papers, all linking theory and practice. I will say a few words more about them, but will not take way too much time. So the first paper comes from the University of Utrecht in the Netherlands, and it looks at the important question of requirements elicitation, and in particular about a method called fit gap analysis, and tries to evaluate and improve that from the viewpoint of grounded theory. The speaker of the 3 authors, Tjerk, Spijkman, Fabiano, Dalpiaz, and Sjaak Brinkkemper, is Tjerk Spijkman, and I would ask him to share his screen now, and we look forward to your talk.
All right, thanks for the introduction. Just starting the screen share at the moment. All right. So thanks for the introduction. As you said, our work is called Requirements Elicitation via Fit Gap Analysis, which a view through the grounded theory lens. It's a collaboration between Utrecht University, specifically the RE Lab, and Pfizer, a company where I'm also employed. And I'll be presenting on behalf of my co-authors. So let's see, there we go. So if we consider the role of requirements engineering in software design, it's traditionally considered a key activity when we're creating a new software product. So for instance, if you have an idea or a request, then you start gathering requirements before you create something. Or when there's already an existing product, then you might be determining your roadmap. So if we take, for example, Microsoft Teams, which had a huge influx of new users recently because of the whole pandemic that we had, they get new requirements and they prioritize and then define how they're going to handle those. Similarly, in a product line like Adobe Elements, Adobe Photoshop, Illustrator, there's a shared set of functionalities, but they all consider a different use case and need to take into account the requirements of their specific user group. But what we saw is that within literature, there's not a lot of focus on fit gap as a requirements engineering source. And we did see it quite a lot within our practice environment. And well, to just give a bit of an introduction of this, it generally goes for business to business software products. We have an schema of that here, where the square is the software product functionality and the kind of Tetris overlay is the process that the customer is trying to get covered by the software product. We see that there's a set of functionalities that aren't really relevant but are part of the software product. And we see that there's those kind of parts of the product that do meet the requirements and will be used, but they might still need to be configured. So you might want to use teams within just your organization or also allow guests. And there's also these kind of parts that are not covered by the product, and they're kind of the gaps within our fit gap. So what we generally observe here is that there's a different market dynamic than there is in like a general user case. So I mentioned Teams a couple of times, and they have a very strong market position because they have a lot of users, and in the end, they're kind of established already. But if we look at like selling a software product from business to business, generally your customer has a lot more power within the negotiation than someone who just buys a single license. So what we observe is that there's generally customer-specific development done and deployment as part of the process for implementation. And this leads to both configuration and customization of the software product. In literature, we do see fit gap mentioned quite a bit, but it's predominantly in the ERP domain. And we argue that it's relevant for any business-to-business software product. So the core definitions for our work are customization and configuration. So just to get that out of the way, I want to cover these again. So we see customization as any change or addition to the functionality available in the standard software product, whereas configuration is the parts that are in the software already, but need to be configured for the customer based on the kind of processes that they have. So if we consider a fit gap analysis, which is generally done as part of the sales cycle of a software product, either before or after selling them and during the implementation parts, we see that there's an existing software product which has a set of functionalities. These generally get discussed by a business analyst with the customer and stakeholders. And the customer and stakeholders are generally considering their own current processes, their goals for buying the software product, and they have their own needs there. Whereas the analyst is aware of what the software product does and what the kind of standard flows are that they cover. And we see that this combination of needs and product functionality ends up as an analysis document, which contains both fits and gaps. Now, these fits can be configuration requirements, can be the customer ask or the analyst determining whether the customer needs a approval flow for certain processes or not, or it can just be out of the box functionality. So if we're talking again about software products like Teams, then it's being able to call other users. Okay, that's just always part of the software. Or there could be gaps, which means that additional development would be needed to meet those customer needs, or they'd have to change their processes, or maybe it's just a bit of expectation management and they'll have to use a separate software product for those kind of things. So that led to our research questions, with our main research question being, how do the contents of such an analysis assist a business analyst in identifying configuration and customization requirements? So we focused here on the transcript because it gave us a tangible artifact to look into, and it's also something we could have available for an automation perspective at a later stage. So the first research question that we had is, how can we categorize the segments in this kind of conversation, and specifically the transcript of it, to support the identification of configuration and customization requirements. The second one was, okay, once we have these categories, which ones are more important to determine and detect within the transcription. So we performed for this grounded theory analysis, specifically the guidelines by Corbin and Strauss 3rd edition, it's presented here. And generally, when you do grounded theory, you're trying to come up with new findings based on the data. So instead of starting from an ID, we really started from an empirical data set from what we observed in practice. So we started from a set of 12 hours of recordings and discovered and refined the node sets through in vivo tagging. This tagging was reviewed by an external party for validity and discussed in meetings. Additionally, we did consistent note taking as is part of grounded theory and discussed these findings periodically within the research team, providing new insights and helping us scope further analysis. So to introduce our case study, it was about accounts payable automation software product, specifically Spijkman, which helps automatically process invoices. We looked into a case for a challenging customer, at least as far as the case company is concerned, with a relatively high amount of customization. It was a total of 12 hours of analysis sessions with a word count of about 80,000. Most of it was a one-on-one with the process owner and the business analyst from the case company, with domain experts joining for specific process parts when their knowledge was required. It was also done before finalizing sales, which generally is the other way around at the case company. So we ended up with a categorization from the grounded theory research. I'll cover 3 of the topics in a bit more detail, and then I'll have to refer to the paper for the others because we're limited in time here. So the first one that we saw was the discussions on the future process, which can either be an generic discussion on it, like in the future, will we do A or B, what's better, or we want to achieve this and that. Or it could be an example which really took a use case and walked them through there based on the future scenarios. Similarly, we saw the current process also in a generic overview or in examples. And an additional note that we saw here were the customer-specific scenarios, which were like the kind of exceptions already mentioned by the customer or the business analyst during the conversations. And these could lead to the need for customization. And we saw the product functionality, which could either be parts of configuration. So the analyst might be asking, okay, do you want approvals for each of your invoices or not? What are the kind of benchmarks that we need to achieve? Those kind of questions, or just managing the expectations by explaining how the product works. So an example for the future process here is the following quote. We have the opportunity to have some of our big vendors send us EDI files or invoice files. So we're debating whether we let these come in as EDI and load them in our ERP, or come in as invoice files for automatic processing by Spijkman. So you see here, there's multiple opportunities, and the customer and business analysts work together to define what the best solution is when using the software product. For this specific one, in the end, the choice was made to let them come in as invoice files because everything would go through a single route then, instead of having multiple different entryways. And for the current process, we also have an example where we see this. The IT department has their own ticketing system for their services. For example, repairs that need to be done. This means they have their own purchase orders, which are not within the system. Now, what this could mean is that the current process has some limitations or constraints for our product. So normally they match purchase orders with the invoices. And we see here that these purchase orders might not be available unless we integrate with that other ticketing system, change the process, or try and find another way around this issue, which could lead to customization if we want to meet this, or to a bit of change management if we need the customer to change their processes. And finally, the example for product functionality. We see here that the interviewee, so the customer, is saying, I think in the demo it was said that you can train the system to, for example, when we see words, tax, freight, or whatever, to automatically add a line for payment. And then we see that the business analyst explains how it actually works. So he says how it works. It will check the tolerances you set it for voucher match automation. So from there, we'll check, is it within my bounds to accept this? And if so, process it. If the shipping makes it go above the percentage or total limits that you set, so say they charge you 600 for shipping, while your gap is 300, it will fail to match. So again, here we see some expectation management. So the business analyst is explaining how the software product approaches this scenario that the interviewee has made assumptions about. And we also see the need for configuration because we're talking about bounds to automatically accept. Well, these need to be configured for that customer. So the other categories that I won't go in too much depth right now because of time constraints that we saw in the transcripts for organization details, product motivation, organization problems, 3 different types of questions, and explicit mentions of requirements. So after doing this grounded theory, we wanted to validate our results because we just needed to compare that to our own bias, and there's always a bit of bias in doing this kind of research. We just wanted to validate with the industry practitioners whether our results were okay and what their thoughts on this categorization was. We did an experiment with 7 industry practitioners within the familiar with the software product, and 36 students as an extra validation set who were taking the RE course in order to have a bigger sample and say more of our results. We then compared the results both individually, so industry practitioners compared to students, and as a whole set. Our experiment consisted of 2 different steps. First, we asked the participants to rate transcript segments from a relevant scale for purpose of documentation. So creating this fit gap document. We had chose a random set of fragments with an even distribution between the categories without showing what category they belong to the participants. And they were randomly selected from a larger set through software tooling. And after rating these fragments, they were also asked to rank the categories in order of importance for an analyst. So the first step was basically this, where they saw the statement or the fragment from the transcript. We also gave definitions for the domain-specific terms in case that people weren't completely familiar with them, mostly for the student participants, and asked to rate them. Do you think this is irrelevant, essential, or somewhere in between for the purpose of documenting this analysis session? What we observed here is 3 categories being most positively rated. So the current process, future process, explicit requirements. And questions was also quite positively rated, but on the second step, it was less highly ranked. So that's why it's positioned a bit lower here. And then for the category ranking, we asked them to, for each of the categories, to put them in an order of, most valuable to least valuable. And we created box plots based on this. And we see the similar top 3 with the current process, future process, and explicit requirements. And then there's organization problem somewhere in between, and the others are following them. So we see that questions is a lot lower on the category ranking than in the segment rating. Aside from that, the findings kind of match in both parts. So from doing this grounded theory, we made a few observations. We saw that there were actually very few explicitly mentioned requirements in the conversation. It's mostly just what's our current process, what are our goals in the future process, and then you'd have to find the requirements from those differences. Also, we saw that the transcript segments in which artifacts are used lose a lot of their value. So in our case study, they were talking about exception invoices. And if you can't actually see the invoice which is being referred to in the conversation, that's an extra challenge and just information you're missing. So creating from this research our hypotheses, we built the implications for research and practice. We saw that from our validation, the most important categories for fit gap analysis are future process, current process, and explicitly mentioned requirements. We also saw that linking back to not a lot of explicit requirements being in the conversations, that the analyst uses bits and pieces of information to specify the requirements. So they look at the current process at the customer, they look at the product functionality, and they combine these into a to-be process and see where the gaps are and formulate the requirements on that. We saw the configuration requirements mainly within parts discussing the product functionality, the future process, and the current process. And the customization requirements were generally from a mismatch within product functionality and the future process, which can be explained by the current process at the customer because they need to be able to continue certain use cases. So an example of this would be that we're currently filling in data and we don't know necessarily all fields from a automation perspective. How can we handle that? So we were interested on the rationale of why we're configuring and customizing software products in these kind of scenarios. And we looked at configuration and saw that it's either a part of the software with multiple possible process flows. So do you want approvals or not? How can we set it up so that it matches your requirements in the process? So when will invoices automatically be processed and when will they need to have an additional check in place? And there are changes that are context related. I have an example of that coming up, and user-defined segments. So for an example of the context related changes, we see here a quote by the customer. So they say, our main office is responsible for processing the invoices of all our offices. We have a centralized accounts payable department. So there's advantages to doing like all your invoices to a single location or to have it split in a office by office situation. And the software product needs to handle that. Which would be a reason for configuration. Then for customization, we pretty much saw two different parts. One is a unique situation for the customer we haven't encountered before. So that's pretty much a gap within your software. And the other one is a workaround for a normal process, which could be considered a gap within the customer's processes. So here they say a lot of utilities, we don't have invoice numbers. So I'm going to generate, well, we enter them ourselves. Is it something the software product can generate, or do we need to enter it manually, leave it blank and then enter it after processing? So here we see that they just don't have an identifier on those invoices. So it's kind of an issue in their process, and they're doing a workaround, and they're expecting to be able to do that workaround with the software product as well. Okay, so to get back to our research questions and reflect on those, we came up with this categorization as part of the first research question. In the implications, we discussed where the configuration customization could mainly be found. And from our validation, we saw that the future process, current process, and explicit requirements deliver the highest value with some mixed findings and questions. And to quickly go through our vision, because I'm running out of time, the fit gap analysis related requirements engineering tooling should present an analyst with relevant segments and an overview of the discussed topics, explore the segments of a transcript, provide an interactive experience, because from what we saw, a fully automated approach is unlikely because it's a non-algorithmic task. And that's it for my presentation. If there's any questions, I'd love to hear them, and thanks for your attention.
Okay, thank you very much. I would like to, I'd like to open up for questions now from the audience. Please raise your hand or write in the chat. Okay, maybe I can start with a quick question while people are still thinking. You had mentioned this one statement about the negative role of artifacts in understanding the transcript. I did not quite understand what you were trying to say there.
Yeah, so I can
essentially the
elaborate
fact
on that.
that you, yeah, that last sentence there, indeed.
Yeah, so pretty much we look at the transcripts of these fit gap analysis, which means that if in that analysis, the business analyst and the customer are discussing an artifact that's not represented in the transcripts. So if we're looking at this from an automation perspective, it's knowledge that the business analyst would have because he was there at the spots, but a software tooling would miss because it doesn't have access to, for instance, those exception invoices that we discussed.
So it would be desirable in those cases to have like samples or so of these artifacts in addition to the textual transcript in order to understand what these guys are talking about. Is that what you are saying?
Yes, partially. And additionally, that it's also an extra challenge if we're, well, currently we did all of this manually for the purpose of, generating theory. But our end goals are to, build kind of requirements engineering tooling that can do part of this automatically. And of course, that tooling would be limited to just a transcript because it can't go through those samples and match them to the parts where they're discussed necessarily.
Okay, maybe another question could be about scalability of this. Does this have anything to do, for example, with the number of users or with the diversity of users?
I'm not sure I get the question, but I think...
Well, the question is, you have this interview of 12 hours for this case study. And I mean, what group of people who have spoken to each other there does it reflect? And I mean, would this scale to a large scale installation where maybe you have different groups of users or so?
Okay, so you mean like a different setting that's less one-on-one, but more a focus group or something like that?
For example.
Yeah, so I think that the categories that we have would still be relevant for those situations because they discuss similar parts of the discussion. An additional challenge that you have is speaker matching in that case, because currently in this one, it's either the analyst or the customer. Whereas in a focus group, you need to consider the backgrounds of everyone. I know there's a tooling to do a lot of like speaker identification, but you still need to consider the backgrounds of everyone. Whereas here, you know, it's either someone with knowledge about the software product or about the customer processes.
Okay, I do not see further questions at the moment. Anna, you have any that have arrived with you?
No, so
okay.
Yeah,
so
maybe we can proceed.
Thanks a lot, and congratulations to a nice talk. And we would pass on to the second talk. We are now switching from the early phase of requirements engineering to the setting of the actual running of systems on systems architecture for real-time data analytics. In this area, the so-called Lambda architecture has been proposed as, let's say, an easy way to combine the advantages of old-scale data warehouses with data stream management as a second branch. So that's the 2 feet of the Greek letter lambda, which then are brought together. But there are some problems with this architecture. And in the second paper, people from the Laboratoire d'Informatique de Bourgogne have analyze this with a method of category theory, which is used from time to time as a very formal and abstract background, which might be interesting for such an architecture. The paper about this has been written by Annabelle Gilly, who will also give the talk together with Eric Leclerc, whom I also see in the audience. Welcome. And Nadine Coulot, which I'm not sure whether I also see her, but I don't have the whole picture in front of me. So I would like to invite Annabelle to share her screen for the talk.
Thank you for the introduction. So I'm Annabelle Gillet. I'm a third-year PhD student at the Lib Laboratory at the University of Burgundy in France. And I will present the Lambda Plus architecture, an evolution of the well-known Lambda architecture. And I will also present formalization that use category theory to study the conservation of properties in composition of components. I will start with an introduction about architecture in general, then about styles and patterns. I will focus on the Lambda architecture. After that, I will present the formalization based on category theory to study the conservation of properties in architectures. I will present also the limits of the Lambda architecture and how we can replace it with the Lambda Plus architecture. And after that, I will conclude the presentation and outline future works. So designing a software architecture is essential when building an information system. To be efficient, the design must guide the overall structure of the information system and define the components and their interactions. The design must also state the properties that the architecture must support, such as, for example, the real-time property or the correctness of the processing. If those properties require some specific technologies, it must also be stated. To help designing architecture, we have styles and patterns that are the representation of common architectural characteristics. There is a slight difference between styles and patterns. Styles are coarse-grained specification of the organization of the architecture. They guide the interaction among components. Each style brings naturally some architectural characteristics, but also impose trade-off on other characteristics. So there is not a style that is better than the other, but solely styles that are better suitable to a given situation than the other. Among famous examples of architecture styles, we can find the layered architecture, the microservices architecture, or the event-driven architecture. On the other hand, the pattern is a specific abstraction of fixed architecture styles that bring a particular set of essential characteristics. It helps to identify which combination of components will be more suited to a context, but also let enough freedom to adapt the implementation to the specificities of the situation. As example, we can find the Blackboard pattern, the model view controller, and the Lambda architecture. So the Lambda architecture was defined by Mars in 2011. Its goal is to compute predefined queries in real time and to take also in consideration the correctness of the processing. And it has also a strong fault tolerance capability. So to do so, the Lambda architecture is composed of 3 layers: the speed layer, the batch layer, and the serving layer. The speed layer is in charge of computing in real time the queries to produce the speed views. But this layer lacks of correctness. So the batch layer is here to compensate this lack of correctness. To do so, it has 2 major roles. First, it stores raw data in the master dataset, and then it processes those data with batch processing to produce the batch views. The master dataset is also responsible for the fault tolerance property to reprocess data if needed. And finally, the serving layer merges the speed and the batch views to answer queries of users. With this specification, the Lambda architecture is able to compute queries in real time in the speed layer and to produce correct results in the batch layer. But those 2 properties are not supported by the overall architecture. We will see with the formalization based on category theory why they are not supported. So the purpose of the formalization is to study the conservation or the discarding of properties in composition of components. It is essential because when building or evolving architecture, we can merge several smaller parts of architecture that can have their own styles and properties. So we must know beforehand what will be the impact on properties. To do so, the category theory has several advantages. The compositions are first-class citizens with morphisms and functors. It is a main advantage because the purpose of the formalization relies on compositions. It also allows the navigation among abstraction levels, so we can represent an architecture at different levels of granularities and then link those different levels. And finally, as category theory is a part of the foundations of mathematics, it doesn't invalidate the other formalization, but instead it allows to switch from a formalization to another. I won't have time in the formalization to explain all the detail of the formalization. Instead, I will try to intuit its mechanisms. If you are interested, you can find more in the paper. So I first need to introduce some notions of category theory. A category is composed of basic elements, a collection of objects, of morphisms that link an object, the domain, to another object, the codomain. Among those morphisms, we have particular morphisms that link an object to itself. They are called identity morphisms. In category theory, we also find functor. A functor maps a category to another category. It has effects on objects and on morphisms. The effect on morphisms have a strong constraint. It is that the domain and the codomain in the source and in the destination category must be the same objects when we apply the functor on them. It is an important constraint because our formalization relies on it. I have two more notions that I need to explain before digging into the formalization. Preorders, that are categories in which between each pair of objects there exists at most one morphism. We use preorders to represent properties. We link the value of the property from the most satisfying to the least satisfying value. And we use the top property represented by a T to use when components are not concerned by a property. The second notion is the one of power sets. Power sets are sets that contain all the subsets of a given set. We use the power sets in a category called components PS to represent the individual components and to then represent the composition by adding a component one by one until the final set that represents the overall architecture. So to apply the formalization, we first have to define the elements that are known. So the morphisms in each category and the effect of functor on individual components to each property. We start with the morphisms. In the components PS category, we have one morphism that goes from the batch layer to the batch serving composition, and another morphism that goes from the serving layer to the batch serving composition. In the correctness and real-time property that are each one category, we have the same morphisms. We have one morphism that goes from the top to true, another that goes from true to false. We have the identity morphisms, and we have a composition that goes from top to false by using existing morphisms. We now define the effect of functors on individual components. The serving layer is not affected neither by the real-time nor the correctness property, so it is mapped to top. And the batch layer supports the correctness property, so it is mapped to true, but not the real-time property, so it is mapped to false. Now that we have stated all the elements that we know, we can use the formalization to deduce the value of the batch serving composition for each property. We start with the correctness property. We rely on the effect of functors on morphisms. So we try to deduce at the same time all the morphism from batch to batch serving and the morphism from serving to batch serving will be transformed in the correctness category. We know that those two morphisms will have the same codomain and that they start from a different domain. So we look for two morphisms. one that starts from true and the other that starts from top, and that will have the same codomain. We have one match, the morphism that goes from top to true, and the identity morphism on true. So from this, we can deduce that the batch serving object will be transformed in the true object in the correctness property. So the batch serving composition will support the correctness property. We use the same mechanism to deduce the value of the batch serving composition in the real-time property. So this time we look for one morphism that starts from false and another that starts from top, and that will have the same codomain. There is also one match, the identity morphism on false, and the composition that goes from top to false. So the batch serving composition doesn't support the real-time property. If we apply the formalization on the overall architecture, we can see that when we merge the batch on the speed views, we cannot support the real-time and the correctness properties at the same time. So the lambda architecture is not a perfect pattern. We will see now its other limits and its connection with the Kappa architecture. First of all, the lambda has been criticized a lot due to its high complexity, because we have to perform the same computation in the speed and in the batch layers, but these two layers have different paradigms. So it induces a high complexity because we need to perform the development twice. It is hard to develop and maintain the architecture in this condition. The use cases of the lambda are also limited. We can only compute predefined queries. So all the processing that we do must be known beforehand. It reduces the flexibility, even if we need a lot of flexibility to process big data. The definition of the pattern also lacks in precision, especially when we merge data in the serving layer. When we deal with unordered data, it can be a hard problem. And finally, the context of creation of the lambda architecture is tightly coupled to the beginning of stream processing systems. Stream processing systems had begun to emerge approximately at the same time as the conception of the lambda architecture. At this time, they had only two levels of data processing guarantee. At most once where data could be never processed, and at least once where data could be processed multiple times. These only two levels of guarantee explain why we couldn't support the correctness property in the speed layer. But since then, the stream processing system had a new level of guarantee that is called effectively once or exactly once. And in this level of guarantee, data are processed once and only once. However, this level of guarantee had to be nuanced because the effect is only visible from an outside point of view of the stream processing system. In the internals, the messages can be reprocessed. So if the processing has side effect, for example, writing in a file, they must be idempotent to support the correctness property in the overall stream processing system. With the evolution of stream processing system, we can replace the lambda architecture with the Kappa architecture. The Kappa architecture is a simplification of the lambda architecture because it keeps only the speed layer. But by doing so, we remove the batch layer on the master dataset, so we lose the fault tolerance property. And the Kappa architecture doesn't add use cases to the lambda architecture. So we propose the lambda plus architecture to replace the lambda architecture. The motivation behind this pattern is to fully take advantage of big data and by adding the flexibility that the lambda architecture lacks. For this, we have identified the duality linked to the variability of big data. This duality is between real-time insight that correspond to predefined and identified needs. They are computed to follow the evolution of data of interest. The second element of the duality are the exploratory analyses. The exploratory analyses can be performed when we want to dig in an anomaly that we have found in the insight, and it can also be used to find new insights that we then can compute in real time. So the objective of the lambda plus architecture is to leverage the duality between real-time insights and exploratory analyses. And it is also to keep the fault tolerance property of the lambda architecture, but also to get rid of the duplication of processing in the speed and batch layers of the lambda architecture. To do so, the lambda plus architecture is composed of 5 main components: the data traffic controller, that can perform a like transformation on data, for example, adding a timestamp, and that organize data into stream to put them to disposal to other components. It can be done with a message-oriented middleware, so the other components can pull data that interest them. The master data set is the same as in the Lambda architecture. It stores raw data to process them in case of failure or if the need have evolved. To avoid the complexity of the Lambda, we don't process data in a batch fashion, but instead we only send them to the streaming ETL components, so it can process them in a stream processing fashion. The streaming ETL components transform and store data in the storage component. The need for more freshness of the last years in a result have outdated the classic batch ETL. So new work focus on performing ETL in real time. The real-time insights component compute the predetermined queries in real time. The correctness and the real time are essential in this component, but with the evolution of stream processing system, it is not a problem anymore. And finally, the storage component supports the exploratory analyses, so it should be flexible enough. It can be, for example, a data warehouse, a data lake, or a polystore. We have formalized the Lambda plus architecture. So it supports the real-time on the correctness property, contrary to the Lambda architecture. The only time when the real-time is not effective is when we reprocess data for the master dataset, but it only happens in case of failure, so it is a trade-off acceptable. We have implemented the Lambda plus architecture in an interdisciplinary project. The goal of this project is to build an observatory of Twitter data to compute the trends, to find the weak signals and the singularities in data. To do so, our data traffic controller is connected to a Twitter API. It then sends data into Kafka. So the data are the raw tweets in a JSON format. We store them in a master dataset that is a Hadoop file system warehouse. Our streaming ETL components populate a polystore that is composed of a relational, a graph, and a time series DBMS. And our real-time insights compute, for example, the trending hashtag or the users that are retweeted the most. We perform various analyses on the polystore. They use with R, Spark, Scala. It can be, for example, tensor decomposition. And this architecture is in production since 2019. So to conclude this talk, I have presented the limits of the Lambda architecture with its high complexity, its limited use cases, and the fact that it cannot support the real-time and the correctness properties at the same time. We propose the Lambda plus architecture to replace it. It avoids the complexity of the Lambda, but still keeps its fault tolerance capability. And it is adapted to the variety of big data by leveraging the duality between exploratory analysis and real-time insight. We also propose the formalization of architecture that is based on the category theory. It allows the study of conservation or discarding in properties in composition of components. As future work, we plan to develop this formalization to add a mean to navigate among abstraction levels, so we can represent components on the internals of components. We want also to verify if an architecture follows a given style or pattern, and we want to extend the property description to handle numerical value. It can be used, for example, to record the execution time of individual components and to see if the overall architecture can really support the real-time property. I thank you for your attention, and if you have any question, I will be happy to answer it.
Okay, thank you very much for this very interesting talk. Again, I would like to open the floor for questions. And since I don't see any hands immediately, I'll start with one myself. You have basically shown that this original Lambda architecture gives, let's say, contradictory results or inconsistent results between this stream layer and the batch layer. Could you maybe go to the slide where you show this lambda plus architecture and give us a short argument again in terms of category theory, why this new architecture does not have this problem?
In fact, the problem of the lambda architecture comes from the serving layer, because we merge the speed on the batch view. So instead of adding the two properties, we discard them, because when we perform the batch computation, we doesn't have the real-time property. And when we perform the speed views, we doesn't have the correctness property. So we also we only have correct result when the batch perform its computation, but in the current result, we have a result that can be incorrect. So it's yeah, I think it's
so what you're arguing is that essentially you have here more or less only the streaming layer, because you convert what is done by batch on the master data set. So you convert that basically to part of the data stream. Is that what this arrow downwards from master data set to streaming ETL shows?
In fact, I think that the lambda architecture was mostly here to compensate the beginning of the stream processing system, because they couldn't produce correct results. But as the stream processing system have evolved, we can perform correct computation in the speed layer. That's why we can replace the lambda architecture by the Kappa architecture. So we take advantage of this to propose the lambda architecture, but also to add more flexibility to the lambda, and to add the exploratory analysis, because it's a main functionality when we deal with big data. When we have a lot of data, we can't know at any time what they are made of. So we need all the time to explore them and to find new insights, and to use those insights to then discover new data. It's an incremental process that the lambda architecture couldn't support in itself.
Okay, so that's this green box at the bottom that you are talking about. All right, are there more questions? Okay, I guess I don't see them at the moment. Yeah, I guess my original question was aimed on this situation where you have this data stream in the middle, the red one coming in, but you also want to link that to, let's say, for example, historical things, like learn whether this new data stream, let's say the weather data from Washington State in the US, how far they are away from historical weather patterns from the last 100 years or something like that, which you probably have in the data, the master data set. Okay, so my scenario that I have in mind when I think about the lambda architecture is not pure stream processing, but it's links stream processing to the content of existing long-term data. I'm wondering whether you have that scenario also in mind, or whether you are mostly interested really in the process, in the meaningful processing of the real-time data that are coming in.
It's a link between I think with a stream processing system, we can't perform all the type of computation. When we need a lot of historical data, it can be hard to link them. But maybe it can be a use case for or to perform them directly on with the exploratory analysis on the storage component.
Okay, thank you. All right. More questions from the audience? I see one. Well, it just says, thank you for your presentation, Anna, very interesting work. So I will join that statement. Thank you very much. I think this is quite interesting and important work to really understand the consistency pattern in modern data management. And then we would come back actually to more the software engineering approaches in the third talk. Thanks again. Because here we are talking about software engineering in the context of software product families or software product lines. Those software product lines have, since they were invented, so to speak, in, I guess, the late 90s, they come together with models. What is the allowed variability, multidimensional models? What is the allowed variability within such a product line? And what this particular paper does is to try to combine these ideas with non-functional requirements. And again, it takes category theory that we have already learned about, so we don't need the introduction again in this talk. Uses category theory to evaluate possible solutions for this combination. The work was done jointly between University of Malaga in Spain and the KTH Royal Institute of Technology in Sweden, Stockholm. It will be presented by Daniel Jesus Munoz, joint work with Lilian Burov, Monica Pinto, and Lydia Fuentes. Please share your screen and go.
Yes. Can you hear me well? Can you hear me?
Yeah,
Yes.
we can hear you.
Okay, good. Oh. I want to access the menu, but the screen is so small. It's closing. See if I can resize the screen. I just cannot access the button to press present. Is there any keyboard combination to
Presenter mode, F5.
Yeah. F5? Okay, I will try. Yeah, perfect. Thank you. You saved my day. Okay, so I will move this. Yeah. Each part of the title is important. We are covering many stuff, but thanks to the previous speakers, and by the way, your talks were really interesting. I don't need to introduce the part of the category theory and not much of the requirements as well. As they mentioned, it was a collaboration from KTH and University of Malaga. It was till the last minute decided because with the COVID, it was difficult as I moved there for an internship, but finally we could do it. So I thank Professor Dilian very much for hosting me and doing every paperwork, because with the current situation was really difficult moving abroad. Let's start with a bit of software product line explanation. This is a really crash course. We have a system, usually a highly configurable system that we want to analyze. Then we have a model that represents that system. And that model is the input to automated reasoners. The basic reasoning that the automated reasoner will do is to generate one solution or to check the satisfiability of that model. And then it will generate, as I said, for example, one product. But another inputs are the user requirements or the developer requirements that constrain the model externally, and also the objective. This is more related to the optimization. If you want the most optimal solutions or near optimal solutions, or also if you want to generate all the possible solutions, is also the default behavior of some reasoners, generate all the possible or valid solutions. Then comes the situation. It comes a client, and this is an imaginary situation, by the way, but it comes a client and asks us, could you analyze our highly configurable system? And obviously, I'm the SPL engineer. Yes, sure. It starts describing the system, and it starts, okay, it has some components and alternatives. Okay, maybe with a SAT solving, I can do it. But it has also arithmetical requirements. Okay, maybe I need to move out to other larger models like SMT or constrained programming models. Okay, it has quality measurements. Okay, maybe a hybrid model because the previous model doesn't support straight ahead quality attributes. And then it has system requirements. Okay, I have cross-tree constraints. And then we have cross-quality requirements. Okay, this is too much. There isn't a single model right now that can do all that and that is connected to an automated reasoner compatible with that. So I did what everyone will do in Sweden when it needs to solve something. I went to the Laplands and asked Santa Claus, what can I do to solve this? And he told me, no way, there is no solution right now. So I needed to think and read the literature, what can I do? And this actually happened in the scenario of the edge computing. Why? Because edge computing deals with like locally distributed computation, and you have many sensors, many variables. It's not like a monolithic coherent system. You have really numerical stuff, cross requirements. It's really, really complex. So we needed a solution to solve this. Then, which is the current trend in modeling in my community? The first one is, and the most common is extending, because we don't have standards yet. We have like consider standards by some parts and others by another part of the community. But the main approach is extending. I have this model we've been using like this way, and we add new functionality. Sometimes they do it to the model, but the reasoner doesn't support it yet. But I will not enter into the reasoning yet. But this is what we usually do. We extend models. Second option is we create new pseudo standards. We take something from this one, something from this, another pseudo standard, let's say pseudo standards A and B, and I create something new that is smaller but more specific for what I'm trying to solve, and maybe it works for that. But you are adding a new pseudo standard. Sorry, I need to press. Also, it's the hybrid model of transformation. I transform one model in A into B, and now it works. Or I use two models and I create something in the middle that interconnect those two models, and then both reasoning, independent reasonings works together. I did this option as well. And then it wasn't enough, it gets too complicated. So we tried the unification. And I mean with unification, not creating new standards to unify everything, but something that will use what already exists in a simple way. So it's an auto-extension. Let's talk about the extensions that we needed to cover. Here we have the variability and quality attributes modeling. Regularly in SPL's models, follow this tree graph-like hierarchical structure. There are some exceptions like the propositional formulas, but I will not enter into that. Some extensions here that you can check are, for example, first of all, the quality model, the quality attribute model. Regularly, you don't find quality attributes integrated on variability models. And they are, and less of all the requirements like performance there or energy consumption. The way we are currently modeling them is like small consensus, is like a list or a set of quality attributes linked with products. So this is, this product takes this time to run. So you are connecting the complete products with quality attributes. Other extensions are, for example, numerical features that you see there on the left and right side. In this case, integers. Why? Traditionally, variability models are Boolean, and you have Boolean logic like cardinality or an XOR. But when you add numericals, you need many more. You need arithmetic. Because you need to consider the constraints, and you have mixed constraints like logic inequalities with mathematical operations. You have also labels, and in this case, clonables. You have to clone their feature Y1 and feature Y2. When you have a label, you can create few instances of that label. So here are many extensions, but to have it clear, this doesn't compile. What I mean that doesn't compile, there isn't a reasoner yet that can do all these things and can understand all these semantics at once. So that's why we need something that unify, because we have one model that takes numericals, another model that takes the Boolean and regular stuff, another for quality attributes. We need something that unifies all these things that are going on and are developing independently. And yeah, we have it here. As they explained it before, but we have category theory to rescue us. If I need to summarize it in a sentence, is the unifier of apparently dissimilar models while abstracting individual specifics. What I mean, it takes what are common between different models. For example, the tree graph-like hierarchical structure that I explained before, and also abstracting from if it is Boolean, if it's arithmetic, and so on. It tries to cover everything and join everything by their common aspects. I won't enter too much into the category explanation because my colleague before explained a little bit how it is. But then we have categories and are formed by objects and arrows. And they represent related spaces. And the objects are extractor classes, and the arrows are the functions between those classes that preserve those structures. They need to comply with identity and associative composition. So that means self relationships and composition of relationships. In my case, we have the functions that map categories. We have something extra. This comes from the applied category theory, so it's a more straight for usage categorical explanation. We have paths, that is a sequence of relationships and a sequence of arrows. We have the generalized elements. In this case, is the select unit of is an arrow, a select unit, the select unit object from to another object. Regularly data types or can be also structure objects. And the instances is the set value function for elements, is giving a true value and a specific value, numerical value, Boolean value to an element, the elements. Something to mention is the flexibility of category theory. A single object can be a category. And a category can be formed and divided into subcategories. So sometimes what you define as a category, it can be an object because it's a single object category in a upper category. Okay, we will use this later on. Then what I propose, simple. Variability models or quality models in general, relational models are categories. The relationships, constraints, requirements are arrows, are the relationship arrows. Features definitions are generalized elements. So that's like the variables in a programming code, and their values, their current value, are the instances. So giving the value to those elements. This is the category of the numerical variability model, that the same example as before, but now is categorized. As you can see, we have the two clones, the ones that were feature Y and feature Y1 and feature Y2, previous example. We have these are T3 and T3 star. The hierarchical relationships are the arrows, parents and child. I omit certain things here to don't complicate the graph so much, like the cardinality, but they are just elements or arrows of the different objects or relationship between categories, because they are also here self relationships. Then we have the objects of the data types. I summarize them with a cross product, but obviously you will have one for the characters, another for the integers, and then you have the string, the name value of different elements forming a category. And then those data types are also relationships. You are just saying that this element, generalized element of this domain, has this domain, is a numerical feature, and then you instance it with a value. And also you have the cross-object constraints. I put them down right there to just don't fill the graph with many crossed relationships and arrows. But yeah, you can. They are also relationships between objects. Then with the quality attribute model, this is more simple. You have a single entity with following its elements follow the domain name value domain. So for example, performance, numerical, an integer value in seconds. And also the self constraints, like non-functional requirements, performance less than 10 seconds. These are arrows with that specific constraint. Then we have the interconnection, because that wasn't also clear on the software problem like yet, and I hope this will help to that. It's how to formalize the connection between the models, the variability models, and the quality attribute model. And then I need to say that in category theory, you need to define, and you can define intermediate objects, intermediate structures. And also the result that you will get from the automated reasoner, you need to define it as a resulting category, because you are just moving and connecting data from one place to another, even if you modify it in the process. And here what we have are the solution spaces. So we have from the left side all the products that we can create, valid products, and on the right we have the measures of those products. What's happening usually in an SPL, you don't have all the products measured. So we have there the subset, the space subset of the products here called complete solutions, to be more formal, that are measured. And you have a bijective relationship, in this case as a function, between the measurements and those specific products. Like for example, this piece of code takes this time to be run. Now, we apply this framework to a hybrid tool that we have, a hybrid modeling tool that we have. It's called the ADAS. ADAS is made for edge computing. As I explained before, is our problem to solve. And as you can see there, we have two main subtrees: is hardware and software on the left side here and here. And then here you have four subtrees: context, programming languages, operating system, and operations. What we're trying here is to represent every type of system in an edge computing environment. And then here we have the quality attributes model. So as I explained before, we have the performance in seconds, and they are connected just with the leaps of the model. Why with the leaps? Because having a hierarchical relationship bottom to top, we already know the trace of the product. So if we know that we have libraries, we also have a context and a software, and we finish on the root. Then applying the framework, we get what we have on the right. As explained before, subtrees are objects. So we have here the hardware object, the software object. And then as subtrees connect context, programming language, operating system, and operations. We have the cardinalities also as arrows. Then something that I explained before about the flexibility, instead of having two related categories like the quality attributes category and the variability, we integrate it as an object, because the quality, as I showed here, the quality attribute model is a single object besides the data types, a single object category. And then we connected them the same way, just by the leaves. So we have some intermediate, it's called solutions, intermediate object that connects leaps from they are considered leaps from the other objects, from the variability, and with the respective metrics. We applied that because that was an example of how the framework works with a real model with data. So this is an edge computing model, but it's not the biggest one, but it works to test and evaluate our solution. As you can see, it's really simple. We have some devices like Bluetooth chipsets and so on. We have different computers that are running them with different CPUs, like the Snapdragon, a Raspberry Pi, etc. Then we'll have different operating systems, and we have different operations like compression or sending, receiving data, and some numerical nodes or features like the data size or the packages when we are compressing that we are sending, how large or short are those patches. And what we deployed and programmed this here on what you can see on the right is just a little snapshot. It's done on the CQL IDE. It's the state-of-the-art canonical functional programming environment. It's used for category theory, and it already allows to model all what I explained before, and also it integrates different solvers. So it allows us to process the framework and also test it and use it for evaluation. So there is a difference on the reasoning process. Before, what we had was, as we can see here, we have the variability model. In our case, was a constraint programming model with a database. All this quality model was a hybrid system, and it was on a database. But then when we move to CQL IDE, what we have is moving from that to a automated theory improver with Bendix for logic and the equations, and hashing, balances, and chasing for the data types and cross-object arrows. So the reasoning process is different, so we expect different performance. A simple run that is generating all the products that are measured gave us 162 products. And each of them has two measures. It has the performance in seconds, and it has the energy rate in watts, giving 324 measurements, and all that in 0.1 seconds. That's much lower than we were getting on this hybrid system, because then you have some intermediate interconnection that really doesn't scale much. Then we have the subcategories. It was decrease the system, decrease the instances to have a shorter model, and also it takes 0.1 seconds. We triple cross the model as well to have a larger in size model, and it took 0.2 seconds. So it's not much more for that increase. Hence, we concluded that this, while we are not measuring the scalability of the IDE itself, but that our model scales linearly on that IDE, and the minimum runtime for it seems to be 0.1 seconds. We tested it on different computers and environments, and the minimum accounting for was 0.1 seconds. Probably because it's a Java application, so it runs interpreted. Then we perform a regular analysis, like trying to maximize, to minimize energy consumption and maximize performance, decreasing the number of seconds that takes to run every possibility. And we've noticed that compressing data increases the energy rate. but also that powerful CPUs barely affects energy consumption, besides if we are compressing. Probably is related with the first caveat. And also that communication peripherals didn't affect much to the communications, but there is a slight difference where the Wi-Fi is a bit more efficient for large data sizes and large batches. And Bluetooth it's more, it consumes less and is faster for small data sizes and batches. Then concluding, the extended variability models with quality requirements can be represented as categorical objects and arrows. Even if it seems a simple definition, it has some workaround when you are transforming one thing to another, but it can be done. And then when you learn it straight ahead, and also that our category theory framework is viable approach, and that is scalable on this concrete SQL IDE. There are many IDEs that you can test it. I can count 3 of them right now that are for production. And also that can support efficient SPLE analysis, because it performs the analysis really fast. And you just need to model, you just need one model. You don't need to have several models, extending models, and so on. And you are using something that already exists, that is category theory. And then as a future work, we want to support more type of extensions analysis, because every time some new case study arises, you need more things to add to those models. And also to integrate quality models. What we did was using quality attributes model, but quality models are also another field of pseudo standards where you have different subtypes of quality, quality subtrees, and so on. Also tested with larger SPLs. There is another field on SPL that it isn't easy to solve. That are the colossal models, colossal SPLs, when you have 10 to the power of 100 different products. So we don't know yet how the IDE and these transformations will work. We are working as well on an automatic transformation tool from variability models to category to this framework, categorical theory variability models. Because for those large models, doing manually as we did for this work is not also the best procedure. It can be done, but it takes time and knowledge. And that was all. I didn't check the time. Hope that I didn't get too much of it. And thank you so much.
Thank you very much for this elaborate talk. You had a little bit more time than the others used, because they have saved some time. So, and you have had the chance to go more into detail, I guess. Yeah, again, I would like to open it up for questions and comments, maybe also by the other presenters. Again, one question. One thing that you have in the paper but not presented in your talk is sort of a comparison. I mean, you have made a nice presentation within the world of category theory, but in the paper you also have a big table. You don't want to show that now, but maybe just make a general argument why this approach is actually better for your purpose of variability analysis than the competition. I mean, you have, please don't show it, because it's really not the point to look at the details. It's maybe you can just make a general answer.
Yeah, sure. Yeah, it's true. When we decided for the category theory, even if it was the most obvious reason, because of its unification background, I didn't know about category theory before. Actually, I get into it following databases works, new kind of categorical databases.
Right.
And then as I didn't know, and category theory is also difficult to understand at first if you are not from the algebraic field. I got many options. Some of them from the SPL community, other ones from the algebraic community. For example, the first solution that we could think of, me and Dillian, was regarding the relational algebra, like the ones for databases and so on. But what we found is that it's not the same, the SQL language that you use in databases, like select, while, and so on, is not the same as the formalized relational algebra. You don't have things like that we will need, like cross-tree constraints in the sense of arithmetics and so on. You don't have many groupings. You don't have the halving. You don't have the joiningly. I mean, the advanced joins. That's not formalized. And then if this doesn't work on databases because it doesn't scale, as databases are more like linear and identity relationships. So we needed to drop the relational algebra. We check also higher order logic, but on higher order logic, because we need to cover that as well with these, we have variability models using higher order logic. You don't have arithmetics, for example. Then the regular variability model was it comes from the 90s, I think. It's called the FEODA. FEODA is the first formal variability model that we have. It didn't work as well because it's a Boolean and Boolean logic type of model. We have also the arithmetics, but on the pure arithmetics, pure calculations like MATLAB, what they were using are pseudo Booleans for the Boolean. So they are using 1 and 0s to reflect true and false instead of using a true solver for Boolean. Something that SQL IDE in this work is doing. It is doing a combination of different reasoners. That's why it's smart enough to know which part must run on this reasoner and on that reasoner. That's why it's fast. I can't think of, I cannot remember. There were a few. There was also propositional logic, I think. But propositional logic is like a subset of the higher order logic. There is as well the algebra of sets, but category theory. There is a category of sets as well. So if you go to the category theory, you go upper the category of sets.
Okay. Thank you. We have actually one more question now by David Benavides. Could you unmute him?
So we have one question. Questions and answers. Hi, Danny. Nice talk. It made me
You should now be able to ask your question.
Okay.
But switch on your microphone, please.
Hello. Do you want me to?
I'm sorry. Can you hear me?
Yes.
I can read it. Hi, Danny. Nice talk. It made me think that what is the added value of using CT for representing configuration variability problems? It's an exercise of conceptualization. Your implementation was done implementing a sort of CT solver. Did you use it or off the shelf? Greetings from Sevilla.
Yeah, I have all there are a few questions. I can answer them one by one. The first one, hello, David. I know him from the University of Sevilla. Nice.
What is the added value of using CT for representing configuration variability problems?
Yeah, exactly. First of all, when you are using this category theory, let's say like a language, like for programming, when you are extending things, you don't need to create something new. Like I will extend this model. Actually, you are not extending the model. You are just programming. You are just modeling something that can be modeled, including like attributes. You are more familiar with attributes. You can do that. And also, you don't need then the problem that I extended this model, but the reasoner is not compatible with it because I need to extend the reasoner to be compatible with that new feature of the capabilities of that model. And it wasn't an exercise of conceptualization. It was a running exercise, a needed for solving. As I mentioned before, I was working with a hybrid solution. Your implementation it is, well, the implementation wasn't you mean the David, you mean the original, the one that I was using a hybrid model, or the new one? The original one was, yes, half it was constraint programming solver plus a database, but this one it's a combination of not city solvers, theorem prover solvers. Some of them are from databases like the CAiSE algorithm. So the SQL ID is using a combination of them. It's similar like other reasoners as SMT, like C3 works. That depending if you are just using Boolean, it runs on a SAT solver, and the if you are using bits are running on the SMT solver. And so on. So it's smart enough to do it. And yeah, off the shelf.
Thank you very much. And David actually has said that he has understood. I would now like to thank all of the speakers and also Anna for technical support for this session, and all the listeners. Well, I guess so for some of you it's late night, and for others it's like myself, it's just another item to continue the day. So I think it was a very interesting session altogether, and I would like to wish all of you a nice conference, and thanks for your contributions.
Thank you very much. Please join the work session. That is a different link.